wanted to talk about what happens when black holes or neutron stars collide. They create something called gravitational waves. And this is a brand new branch of astronomy that only just opened up in the past couple of years. And it's a totally new way to do astronomy that does not rely on light at all. So, remember we talked about space-time. Imagine our whole universe is like a fabric that we can stretch. That's the fabric of space-time. And when you place really massive objects on that fabric, the fabric warps. Okay. Now, space-time should significantly stretch around two massive black holes or neutron stars that orbit each other. As these objects are orbiting each other, and when they collide, they send out ripples on the fabric of space-time. So imagine it just being like whenever you toss a pebble into water, and that water creates these little ripples on the surface of the water. Same thing happens when you've got two very massive bodies that are stretching space-time already, but then they're orbiting super fast around each other. They send out these ripples like the waves on the surface of water across the fabric of space-time. Those ripples are felt a long distance away from where those things are orbiting each other. And whenever they collide, get really close to each other, and whenever they collide, we can observe now that signal. So here we have two neutron stars that are orbiting each other. As they do that, they create these ripples in space-time. And as they start getting closer and closer to each other, they're going to orbit each other faster and faster and faster and faster. And as they do that, they get closer and closer and closer, and they eventually merge with each other. Okay, and that is our neutron star or black hole merger. And these can be now detected by special detectors. So these ripples can be observed at Earth with a new detector called LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory. Okay, and these can detect, this observatory can detect a stretching of the Earth caused by a passing gravitational wave of less than 10/10,000th of the diameter of a proton. That's crazy. Less than 10/10,000th of the diameter of a proton, this device can catch. Now, as these gravitational waves are moving throughout our universe, they can actually cause objects that they encounter and that these waves pass through to stretch and contract ever so slightly. Stretch and contract on a scale of less than 10/10,000th of the diameter of a proton, which this detector right here can observe. Okay, so in LIGO, you've got these two long arms, okay? And in those arms, you have a laser. And at the end of it, there's like a mirror that can detect changes, stretches in the length of this arm right here, these long arms on the scale of 10/10,000th the diameter of a proton. And whenever they catch these events, that is a signature of a merger of either two neutron stars or two black holes, or maybe even be the merger of a black hole with a neutron star. So as these gravitational waves pass an observer, or the LIGO observatory, that observer will find space-time, or the fabric of space-time, to be distorted by the effects of strain, okay? And the distances, when these gravitational waves are passing through an object, the distances between objects increase and decrease rhythmically as the wave passes at a frequency equal to that of the wave. So here's an example of what happens when a gravitational wave passes through an object. You get some stretching in one direction and then some contraction in the other direction, sort of a push and a pull, and that can be detected by those long arms of the LIGO detector. So what we have here are two plots of these gravitational waves passing through that LIGO detector. This top one here is a signature from the collision of two, or the merger of two massive black holes, and this one down here is the merger of two neutron stars. So what we've got plotted here is what we call the strain. That's this distortion of space-time as these black holes orbit closer and closer and closer to each other until they eventually merge. And then on the horizontal axis here is the time. So out here, our two black holes are separated from each other, and then as those objects get closer and closer to each other, this amplitude here of this waveform, the height of this waveform, gets higher and higher and higher, and then the distance between these consecutive peaks in the waveform get closer and closer and closer as those objects spin closer and closer and closer to each other until they finally merge right here, okay? So this is the signature that's detected of two black holes merging with each other to form one massive black hole. And then down here is the signature of two neutron stars spiraling. And this is all really kind of squeezed in here. If we expanded this signature out even further, you would actually be able to make out the peaks and the troughs here of this signal. I went to the website that had the address there on that previous slide that we were just on. And here they've taken those waveforms that we just saw and translated them into sound so that we can hear the frequency of those waveforms as those objects get closer and closer to each other. And so let's listen to this one, which was the neutron star merger, that last one that we saw. Yeah, it's kind of cute. So as the neutron stars spin closer and closer and closer to each other, the frequency of that waveform gets higher and higher and higher until they merge. At the moment they merge, that frequency stops, okay? So they're warping space-time, and the further and further and further they spiral into each other, that warping of space-time is that signature we see as the stretching of those long arms in the LIGO detector, the stretching of Earth as those ripples in space-time pass through Earth, okay? And we can translate the frequency of those waveforms that are coming through Earth into sound. Frequency is how often does something pass you per time. And so if the frequency goes up, that means that that waveform is passing through us much, much more quickly. There. So as those objects are spinning toward each other, the frequency of that waveform gets higher and higher and higher until they merge, okay? That is the signature of a merger of these black holes or of these neutron stars. And it's a whole new way for us to study the universe. This is called gravitational wave astronomy. Okay, so far, at least 15 black hole and neutron star mergers have been detected through these gravitational waves. This field of gravitational wave studies is very new and has opened a whole new branch of astronomy where no telescope is required. We can learn more about our universe without even needing the electromagnetic spectrum. So here's the actual signal that these detectors are capturing. One of these detectors is in Washington and the other one is in Livingston, Louisiana. So these graphs up here on top are the actual raw data that those detectors caught. And so we see here the fluctuating waveform, and then you fit a model to it. We do that in astronomy. You fit a model to it to get a smoother curve here, okay? And that is the signature of two objects, massive objects, either a neutron star or a black hole colliding. And as they get closer and closer and closer to each other, the distance between the peaks in these troughs gets shorter. Thus the frequency is also gonna get higher. That's the whoop that we heard, okay? And that's called a chirp whenever you're thinking about gravitational wave astronomy. And so here is the plot of that chirp. We've got the frequency of those gravitational waves as they are moving through the Earth as a function of time. And so we've got the frequency is increasing as those two objects are swirling into each other. And then we lose the signal just slightly after those two objects finally merge to become one. This whole process happens very, 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 very quickly, and we're only capturing the last literally few seconds before these objects slam into each other and merge into one. And so here is actually, it's a little video that we can watch to further illustrate this process. So here we've got two black holes that are going to merge, two black holes that are spinning around each other, orbiting each other, but they've got strong gravitational forces, and those gravitational forces are pulling them closer and closer together. And you see that as they get closer and closer together, they spin around each other much, much faster, okay? And we'll see that as an increase in frequency of that signal, the gravitational wave signal, and then eventually they merge together. And then you see here, we've got the ripples that are going out through space-time. And that is the signal that we detect at Earth with these new gravitational wave detectors.